Hey, top of your life math and history, and we are going to take a look at the movement of a graph. So in the past few videos, we learned about like the stuff on final velocity. We also learned about this and that. But also, sometimes we like to put things on a graph to visualize how things interact with each other and things how they move. So, if you remember from like middle school, or possibly like your 9th grade algebra year, you've probably seen like graphs with X and Y on it. And you probably learned how to graph the graphs and understand slopes. And we probably remember that slope represents rise divided by run. We rise, run, rise, run, rise, run, just like walking a bunch of stairs. But when you talk about your slope, you talk about the line that is touching and intersecting them. Sometimes you'll see the equation y equals mx plus b, which is your slope-intercept equation. Not only that, if you wanted to find your letter m, or find what your slope was between this point and that point, then you would do your m would equal your second y by coordinate, subtract by your first y by coordinate, divide by your second x of coordinate, subtract that by your first x of coordinate. So that is what we learned about slope in the past, but hang on, how are we going to understand how to find the movement of a graph by visualizing literally on a graph? So, when we visualize it, it's kind of easier said than done. Because if you look at the x-axis, or your horizontal axis, that represents time. That is how long it takes for the object to move, or make its own interaction. And on the y-axis, if I turn it around, it says position, where the object is positioned. So it's easier said than done. Assuming this green marker represents your origin. And what we want to do is, let's say we drive a car, and that car we drive is going to go in a neighborhood. And in that neighborhood, we're going to drive, let's say, 60 meters. So when we drive 60 meters, we're going to drive forward in a constant rate. So let's see what happens. So Mario drives the car 60 meters in a constant rate. What he does is he starts driving here, but doesn't get to here, because that's instant, which is impossible. Even if we had like light speed hyperdrive and starships, that would still not be possible. So what would happen is he would go in a straight line, going all the way to 60 meters, and then he crashes the car right there. So, when we talk about this picture or this graph, we're going to explain that he drives forward in a constant rate to 60 meters, which is a positive slope, for example. So now, instead of being at 0 meters, he's now at 60 meters away from our reference point, and it took some kind of time. We're not going to calculate what time, but let's say it was 6 seconds. So that is an example of an object moving from the reference point to another point. But what happens if Mario wants to return back to that reference point, here to there? Well, the graph's going to look a little bit different. So what he does is he's going to try and drive the car back to where it started. So, assuming we reset the t as in time in 0 seconds, so our stopwatch goes back to 0. Let's see what happens when he drives back.
Let's go.
So what Mario just did is he goes from 60 meters back to 0. But let's say it took the same time. So instead of going a positive slope, we're going to create a negative slope. Because from 60 all the way back to 0 takes some kind of time. So that means, let's say he went 60 seconds. So from here back to there, it took 60 seconds. But even though he's still moving forward, he is going back to where he came from. So he's going back, which means he's now back at where he started. That's why we have a negative slope. But what happens if we want to combine the two graphs? What happens if Mario instead wants to do two directions in one run? Let's see what happens. So what Mario has to do is, what he did is he went from 0 to 60 in some given time. Let's say from 0 to 60, he's going to move to 60 meters, and that is going to be, let's say, 6 seconds. So from here to here is 6 seconds. But then, his run isn't over yet. He still has to go back, meaning that he's going to go down like this. We're going to say that that is going to be, let's say, 4 seconds. So his total runtime was 10 seconds. So this is very simple, because when Mario goes from 0 to 60, he goes up here, positive slope. When he comes back, even though he's still walking forward, he comes to a negative slope, because it's referencing to where he started. Yeah, that explains the movement on a graph. I hope this video has helped you understand the physics of moving on a graph and why we can visualize and see how an object moves from a reference point.